Assalamu alaikum students, welcome to my channel Physics with Hasnain. Today we will study equilibrium, types of equilibrium. There are different types of equilibrium in statistical mechanics, or we deal with it in thermodynamics often. There are three types of it: thermal equilibrium, mechanical equilibrium, and particle equilibrium. We will study one by one. Equilibrium in a system of particles. It is a condition in which macro properties such as temperature, pressure, and number of particles are constants. This is reached when three of the following conditions are reached. First one is each one of the possible microstates of a system is equally likely to occur. The second is the system's internal dynamics are such that the microstates of the system are continually changing. Given enough time, the third property is given enough time, the system will explore all possible microstates and spend an equal time in each of them. Given these three conditions, we can write one mathematical form obeying these conditions. It is it is delta S, where S is entropy. This is the one mathematical condition or form which can explain all these three conditions. It is because above three conditions implies system should have a maximum number of microstates, or in other words, maximum entropy. Because entropy is a measure of number of microstates, let me write it down here. Entropy is measure of number of possible microstates. It is a definition of entropy. We can prove equivalence of these conditions and zero change in entropy by a contradiction. Suppose entropy is increasing, which means the system is exploring more possible microstates in which it can be. This implies there is more probability in newer states explored by the system. This is against our first condition here, which is each one of the possible microstates of a system is equally likely to occur. So therefore, the form for equilibrium will be this. Change in entropy will be zero. From now we will write this mathematical form as a condition, as a single condition for equilibrium in a system of particles. Now we see thermal equilibrium. It is the type of equilibrium in which temperature remains constant. Suppose here we have two systems of particles separated by a stationary wall which fixes their volume, but they are still thermally connected and can interchange energy between them. So system 1 has entropy S1 while system 2 has entropy S2. This is S2. The total change in entropy is written as delta S1 plus delta S2. At equilibrium, the total change in entropy should be equal to 0, and because in this case entropy of the system varies due to only flow of energy from one system to another, therefore we can write the above equation as partial S1 divided by partial U1 delta U1 plus partial S2 divided by partial U2 delta U2 equal to 0, where U1 and U2 are internal energies of the systems S1 and S2 respectively. Since total energy of the systems, both two systems should remain constant, then we can write delta U1 plus U2 equal to 0, or it implies delta U1 equal to delta negative of delta U2. Now we put the value of U2 here, and this will become, and so these cancels each other, and we are left with only now. This equation shows there is a balance between transfer of energy from one system to another. Each system, here we have systems, both systems, each system absorbs as much energy as it releases to another system. This happens at thermal equilibrium when temperatures of both systems are equal. So we make both sides of this equation equal to the temperatures of both systems. So we can write partial S1 over partial U1 equal to 1 over temperature T1. This T1 is the temperature of system 1, and 1 over T2 is equal to partial S2 divided by partial U2. These two are equivalent and these two are equal. So at equilibrium, both temperatures are equal. Now suppose T1 is greater than T2 and the both systems are not in equilibrium. At this this is the case when total change in entropy should be greater than 0. As from second law of thermodynamics, total entropy change should be greater than 0 or equal to 0, because this is not an equilibrium. At this case, when T1 is greater than T2, so it should be greater than 0. and this equation. This equation will be solved and can be written as partial S1 divided by partial U1 negative of partial S2 divided by partial U2 into U1 delta U1 from here greater than equal to 0. So the above equation, this this can be solved and can be written as like this. We have already seen that partial S1 by partial U1 is equal to 1 over T1, and similarly for system S2. So we can write it as 1 over T1 negative of 1 over T2 delta U1. But because temperature T2 is less than T1, we have written this condition here. So for the whole expression to be greater than 0, delta U1 should be negative, because both minus signs cancel each other. Delta U1 is negative. What this is mean is that energy is flowing from system S1 to S2. System S1 has temperature T1 and T2. T1 is greater than T2, so the energy is flowing from the system S1 into system S2. Now our next topic is mechanical equilibrium. It is the type of equilibrium in which pressure remains constant. Similarly, we have two systems here as with entropy S1 and S2, and we required the total entropy should be 0. Entropy basically is the function of total energy, internal energy, volume, and number of particles. In this situation, we have set the temperature of system 1 and temperature of system 2 equal, so that both systems are thermally in equilibrium and there is no transfer of energy between them. However, the wall between them now can move in order to change the volume of both systems. It is movable wall. Now volume isn't a constant now. However, the number of particles in both systems are constants. No particle can enter from one system into another. So using chain rule, we can write partial S1 divided by partial V1 and delta V1 plus partial S2 divided by V2 delta V2 equal to 0. Here V1 and V2 are the volumes of systems S1 and S2. Now again similarly, the total volume of the system, both systems should be constant. V1 plus V2 is the total volume. This volume is not changing, so we can write V1 delta V1 equal to negative of delta V2, or we can write this one V2 or this one V1. Now we put this value of V2 here, and the above equation will become partial S1 partial V1 delta V1 equal to partial S2 divided by partial V2 delta V1. Now we can divide delta V1 on both sides, and we are left with this equation can be set equal to pressure divided by temperature. This is the pressure of system 2, and this is the temperature of system system 2 T2, and if the temperature of both systems are equal, we have P1 is equal to P2. This is another form of equilibrium, and it is known as mechanical equilibrium. Now we said our system has both an equilibrium, thermal and mechanical equilibrium, but there is another form of equilibrium which is particle equilibrium. In this equilibrium, we allow both systems to interchange their particles between them. Suppose system 1 has hydrogen gas while the system 2 has helium gas. The particles between and both systems are of different kind, and they now can interchange their particles between them. By similar procedure, we can set the total number of particles in both systems constant, and n1 is the number of hydrogen atoms, and N2 is the number of helium atoms in system 2. And again, by similar process, we can um, solve as system partial S1 partial N1. This equation is solved when volume and internal energy are both set as constant, and this equation shows that the number of hydrogen particles moving from system 1 into system 2 are equal to the number of hydrogen particles coming from system S into system S1, and similar explanation for helium atoms. In this case, we can set both of these expressions equal to negative of mu 1 divided by T1, and this is equal to negative mu 1 divided by T1, T2. Here T1 and T2 are temperatures of both systems. Why? This mu1 and this is mu2. This mu1 and mu2 are known as chemical potential, and when the temperature of both systems are equal, we have mu1 equal to mu2, and this is known as chemical potential. This chemical potential can be defined as the amount of energy increased or decreased when we add a particle in the system or reduce one single particle from the system.